So this is joint work with John and Sigal, and I'm not going to be talking about auctions. So what I want to talk about today is present bias. So present bias is one of the earliest behavioral biases that was studied, and it's the tendency to value time in the present more than time in the future. And so this leads to things like procrastination or task abandonment, where you plan to get something done, but halfway through you realize it's too much work and you stop. And one example is maybe familiar to many of us is a gym membership. When you decide you're going to go in for your New Year's resolution, get a gym membership, but somehow when the time actually comes to go to the gym, you never end up doing it. And actually, there was a study that was done. There was a choice between getting a gym membership for $70 a month or paying $10 a visit to the gym. And they found that people who paid $70 a month visited the gym on average 4.3 times. And so people are not good at estimating how much effort they're willing to put in for things. Yeah?
Do they know how often people went to sign up for $10 ago?
I mean, it's self-selection, so probably not comparable, but I actually don't have that number. Okay, and the key question I want you to keep in mind today during this talk is what the interplay is between bias and planning. Because with this gym membership example I gave you, it wasn't just that people didn't want to go to the gym, it's also that they planned as if they would want to go to the gym and ended up not going. So there is some interplay here between lack of motivation and this bias and actually planning around it. And so for this talk, I'll give some background on present bias and a model for which to think about this. And also I'll define this term that I'm using here, sophistication, what this means. And then we'll talk about when it's good, when it's bad, and how its negative effects can be mitigated. Okay, so let's get started. So the way that this model is going to work is we're going to take tasks and turn them into directed acyclic graphs. And so the way we'll do this is we'll put costs on edges. And so you can think of this as each edge corresponds to an action with an associated cost, and each node corresponds to a state of being or a state of completion of this task. And for now, the model will be you start at node S, you need to move to node T, and along the way, you don't want to incur a lot of cost. Now, you might say, well, this is easy. The optimal thing to do is just take the shortest path, which is true, but humans are often not optimal. And so we'll see that with these present bias agents end up not taking the shortest path, but the question is, what are they doing instead? Okay, so for example, let's say you have some work to do. Maybe you need to prepare a talk, and you can either do this Thursday, Friday, or Saturday. And the costs associated with doing things on each day is the opportunity cost for what you could be doing instead. So on Thursday, maybe you're doing some light reading, and to you, this has an opportunity cost of 3. On Friday, you're watching a great movie, so this has an opportunity cost of 5. And on Saturday, you really want to be proving some theorems that has an opportunity cost of 9 to you. And so it turns out that this is actually exactly the graph from the previous slide. You started at S, which is Thursday. You can either work now for a cost of 3, wait till Friday, where you can do it for a cost of 5, or defer until Saturday. Okay, and so now how do present bias agents traverse graphs like this? Well, the traditional model for present bias is that the outgoing edges, or the immediate costs that you're about to incur, get multiplied out by this factor of B, which is your bias parameter. Okay? And the way agents work is they try to minimize perceived cost. Where by perceived cost, I mean according to this bias parameter B. So let me be a little bit more specific about that. I'm going to define perceived cost as B times the cost of the immediate edge, the work that you're about to put in, plus the cost of the remaining path after this immediate edge. So this X, let's say this agent is at U, is considering going to V. This looks like it costs B times X, and then from V it would have to incur some cost. Okay? But I'm being a little vague about what I mean by from V it has to incur some cost, because what is the path going to be once it gets to V? Right? The agent needs to know what this remaining path is going to be before it can actually evaluate what the cost is. And what if there are multiple paths from V to T? Now, this is a little confusing. So the way that we're going to resolve this is by turning to behavioral economics literature and looking at the distinction between what are called naive and sophisticated agents. Okay? So naive agents are by definition unaware that they are biased. They believe that they are optimal. Sophisticated agents, on the other hand, are aware that they have this bias. And this actually does not mean they can eliminate it. And this is actually something that I had a lot of trouble understanding the first time I looked at this. But essentially, it means the following. As a sophisticated agent, I really don't want to work right now. However, I'm smart enough to know that tomorrow I still won't want to get any work done. Okay? So this doesn't change the fact that I don't want to work now, but it just makes me better at planning for the future. Okay? So the way that this is going to translate into our model is that when evaluating this term, cost of the remaining path, naive agents plan as if they'll act optimally, so they plan as if they are going to take the shortest path. Sophisticated agents actually plan the way that they're going to act. Okay? And so what they do is they recursively compute what all their future decisions are going to be. And then they use their knowledge of their future decisions to make better plans for the present. And so I'll get to an example of exactly what that looks like. But let's go back to this thing that I was talking about before about bias and poor planning. Here we have naive agents who are biased, and they suffer from poor planning because the plans that they make are not actually what they end up doing. But by definition, sophisticated agents know what their future actions will be, and therefore their plans are exactly the same as their future actions. Okay? And whereas naive agents are time inconsistent in that they plan to do one thing and do something else, sophisticated agents are time consistent. Whatever they plan to do is what they end up doing. And so now we've separated out the effects of the bias on its own from the bias and the poor planning combined together. Okay? And so let's look at what this actually means in our example. But first, I'm going to be a little bit more specific about what this recursive planning looks like. The rule will be in reverse topological order. For every node, it'll pick the outgoing edge that it would follow if it were to go to that node. Okay? And it does this by choosing the edge that leads to the lowest perceived cost, where again, perceived cost is b times the cost of the immediate edge plus the cost of the remaining path. Okay? But the nice thing is that we have this invariant, because we're doing this in reverse topological order, that at every node, when we're at a node, for all future nodes, we know the path from that future node to t, and thus there's no ambiguity about this cost of the remaining path term. Okay? So at t, the agent knows what its actions would be. It would stay at t. At w, there's only one outgoing edge, so the agent would have to take that edge. At v, there's two outgoing edges, so it would do some cost evaluation and decide, from v, I would go to t. Okay, I've intentionally not put numbers on these edges, but imagine that there were. Now at u, the important thing here is that it has a choice between going to w or to v. Okay, but the agent knows that if I were to go to w, I would go directly to t from there. If I were to go to v, then I would go directly to t from there. And thus this edge from v to w, actually, we can pretend that it doesn't exist because the sophisticated agent knows it would never actually end up taking that edge. Okay? And so using this procedure, let's say the agent chooses to go from u to w to t. And again, now it knows that it would never actually take the u to v edge. Okay? And so going back to our original example, let's look at what a naive agent does in comparison to a sophisticated agent. So the naive agent on Thursday says, working today seems like it looks like it has a cost of 6. And I'm using a bias parameter b equals 2 for these examples. Okay, so working today has a perceived cost of 6, but procrastinating until Friday has a perceived cost of 5. So what's the agent going to do? It'll say, I'd rather do this work on Friday. And so it procrastinates. Okay, but then on Friday, it faces a similar choice. Right? It's choosing between a perceived cost of 10, which is working on Friday, or a perceived cost of 9, which is deferring until Saturday. And so again, the naive agent says, well, I'd rather end up working on Saturday instead. Okay? And so this naive agent will actually end up working on Saturday and incurring a cost of 9. Okay? What's the problem here? The problem and what led this agent to mess up so badly is that on Thursday, it mistakenly believed that it would actually get its work done on Friday. But when the time came, it didn't actually end up following through with that plan. And John and Segal showed that just by extending the simple example out, you can make things exponentially bad in the worst case for the naive agent. Okay? So in contrast, let's look at what a sophisticated agent is going to do. So on Thursday, it faces the same decision. Either I work today or I don't. But because the sophisticated agent reasons accurately about the future, before it can make this decision, it says, if this were Friday, what would I be doing? Okay? And it says, if I wait until Friday, on Friday I'll have the chance between working, which looks like 10, or procrastinating, which looks like 9. Okay? And so the sophisticated agent realizes, in fact, if I wait until Friday, I'll end up waiting until Saturday. And thus, working on Friday is actually not even an option. So the choice is actually between working on Thursday and Saturday, to which the sophisticated agent says, I'd rather work on Thursday, even though it still has this bias. It still perceives the cost of working to be 2 times 3. This just is still less than 9. Okay, so in this particular example, this sophisticated agent has actually behaved optimally. Okay? And so the question that we want to ask is, how bad does this get? How bad can a sophisticated agent be? It seems like it's doing pretty well here. Right? And so this comes back to our question of, when is sophistication good? And so the way that we're going to measure performance is we're going to define the cost ratio to be the ratio between cost incurred by the agent versus optimal cost. And as mentioned before, this is exponentially bad in the worst case for a naive agent. A straightforward example shows that it can be at least as bad as a factor of B for a sophisticated agent, simply because it would rather work tomorrow than today. Okay? And so we worked out more complicated examples, and it actually turns out that this holds for all examples, this factor of B. In every instance, in the worst case, a sophisticated agent is within a factor of B of optimal. Okay, so this is kind of surprising. What it's really telling us is that both naive and sophisticated agents are biased. The only difference is that naive agents are poor planners, whereas sophisticated agents are not. And so it's actually this poor planning that leads to this terrible performance for naive agents. And I'm going to walk through a quick proof of why this is the case. It's pretty straightforward. To do so, I'm going to introduce a little bit of notation. Let's say C sub S of V is the true cost that a sophisticated agent, yeah.
You assume that the graphs don't have circles? So
Yes, these are all going to be,
otherwise it can be infinity.
yeah, we're doing only directed acyclic graphs. Yeah. So C sub S of V is going to be the true cost for a sophisticated agent to get from V to T. C sub O will be the optimal cost. And I'm going to claim that for every node, C sub
True cost is true perceived cost?
true cost evaluated by the numbers on the graph. Not because sum of edge weights, yeah. The problem with measuring things by perceived cost is that perceived cost actually changes over time. It's not, so the valuations are not time consistent. So this is the only way to measure it. For every node, the true cost for the sophisticated agent is going to be within a factor of B of optimal. Okay, so for this example, let's say the agent is at some node U. The optimal thing to do is to go to V, but instead the sophisticated agent chooses to go to W. Okay, so let's see how this induction works. The perceived cost of going from U to V and then to T for the sophisticated agent is given by B times X plus whatever cost it will incur from V, which by induction we can bound as a factor of V of optimal, or a factor of B of optimal. Okay? So this is the perceived cost of going through V. The agent instead decides to go through W. Why? Because the perceived cost must be no more. Okay? However, the true cost is always no more than the perceived cost, because this is simply, the perceived cost is just true cost, but with the first edge weight bumped up by B. Okay? And this actually just completes the proof. So relatively straightforward induction gives you this result. Okay, so to summarize this, naive agents are...
The perceived cost is less than B times C0. It's stronger than what you stated.
Say that again?
Your result is that the perceived cost, which is higher than the true cost, is less than B times C0.
So you can have zeros on the... If X is 0, then this is tight. Because the perceived cost and the true cost are the same.
Yeah, but I'm saying it's a stronger statement.
So this example shows that this is the best bound you can get.
Because essentially from the statement itself, it says that it's a B squared. Perceived cost is no more than B squared. We're asking to prove that it's only B times C0.
It gives you B as a lower bound.
This is a lower bound of B.
It's the lower bound of B on the actual cost, but what...
I'm saying the bound applies to the perceived cost, which is always higher.
Oh, that's true, yeah.
It's a better result and it's a better way to state. Because otherwise it sounds as if the perceived cost could be even B squared times C0. That's all I'm saying.
Okay, I see what you're saying. Thanks. Okay, so summarizing, the naive agents are unaware of their bias. They make time inconsistent plans, and this leads to an exponential cost ratio. Sophisticated agents are aware of their bias, their plans are time consistent, and therefore they get a constant cost ratio. Okay? So as a side note, we'll briefly talk about what happens if the agent doesn't exactly know their own bias. What if they have a true bias, but they also have some believed bias B prime? It turns out this is a generalization of naive and sophisticated agents. Naive agents have a believed bias of 1 because they think they're optimal. Sophisticated agents have a believed bias of B because they know exactly what their bias is. So you could ask what happens for other values of B prime. And it turns out that there's this sharp transition such that if you underestimate your bias, if B prime is smaller than B, things are still exponentially bad in the worst case. If you overestimate your bias, B prime is larger than B, then your cost ratio is still bounded by B prime. Okay, so what this is saying is it's much safer to overestimate how biased you are, plan as if you're really terrible, than to underestimate it. Okay, so we've seen when sophistication is good. Now the question is, what's the catch, right? When is it bad? And it turns out that we've only been looking at cost minimization environments, but you can consider reward maximization environments as well. So let's say instead of costs on the edges, we start throwing rewards on there. Okay? It's been noted qualitatively that sophisticated agents seem to do poorly when it comes to trying to maximize rewards. Okay? And intuitively, here's the way to think about it. Let's say there's some scenario where rewards are growing over time. Maybe you're collecting interest.
Can I ask a question about the previous scenario about cost minimization?
Yes.
Does it ever happen in cost minimization that a naive agent performs better than a sophisticated agent?
Yes. So sophisticated agents are not strictly better in all examples. If you look at the paper, there are examples in which naive agents in that particular example perform better. Okay, so if we're thinking about a situation where maybe you're accumulating interest, the analog of procrastination for the
Better, sorry, just to perform better according to true cost or perceived cost?
true cost.
Not perceived.
That's a good question. I'd have to go back and look at it. I don't remember the example off the top of my head. So the analog of procrastination in this reward setting is greed. Present bias agents would rather get rewards as soon as possible, even when they might get more rewards by waiting for a little while. And so the way that sophisticated agents work in this scenario is that they don't trust their future selves. They know that their future selves are greedy. So they say, there's no point waiting for my future self to collect the rewards because they're just going to prematurely collect them anyways. I might as well take them now. Okay, so I'm going to go through an example. Let's say we have this familiar looking graph, and now my bias parameter is 3. And this is the kind, you can think of this as some sort of interest accumulating scenario. Let's look at how the sophisticated agent plans. So it's, again, going backwards recursively from the graph. And so the first place it would have to make a decision is at V4. And so the decision is between 16 now and 32 later. And so to a biased agent, 16 now looks better than 32 later. So the agent says, if I were to go to V4, I would actually collect the rewards right away and go straight from V4 to T. Okay? But now, as we continue backwards, at V3, the choice is between 8 now, or it could delay for a day and go to V4. But it knows that at V4, it's not going to end up making it to V5. It'll just go straight to T. So the choice is actually between 8 now and 16 later. And given that choice, again, the agent would prefer 8 now. And so this actually continues all the way back through the entire graph. And you find that the agent would rather just go directly from S to T. This is what happens for a sophisticated agent. Okay, so what happened? We actually can make this exponentially bad just by extending this fan out as far as we want. And so there's this kind of weird duality where in the cost minimization scenario, sophisticated agents are bounded by a constant factor and naive agents are exponentially bad. In reward maximization scenarios, the opposite is actually true. You can show that naive agents are within a factor of B from optimal, whereas sophisticated agents can be exponentially bad. Okay? So this is a somewhat surprising result given that what we've seen about sophisticated agents before. So where's the silver lining here? What can you do about this exponential reward ratio? So we turn to what are known as commitment devices. Commitment devices, you can think of them as an action that you take now to mitigate the bias of your future self. Okay? Some classic examples include, for example, Odysseus tying himself to a mast so he wouldn't fall victim to the sirens. He's preventing himself from taking some future actions that might have harmful effects. Similarly, you can think of browser extensions that block your Facebook newsfeed as an action that you're taking now to prevent your future self from taking harmful actions. Okay, so it's really about preventing these selfish choices that our future selves might make. And one particular one that we looked at is called choice reduction, which is just preventing yourself from taking possible actions, and we model that by saying remove some edges from the graph. And so if we turn back to our previous example, let's say we remove this edge from V4 to T. And now we look at how a sophisticated agent would perform here. Now the first decision that would have to be made is at V3, we can either have 8 now or 32 later. And even with the bias, 32 later seems better than 8 now. And so at V3, the agent would actually end up continuing on to V4 and collect this full reward of 32. And now the same reasoning applies at V2, where it's again a choice between 4 now or 32 later. Because we know that if we were to make it to V3, we would collect this full reward of 32. And again, this continues all the way back. And in this example, the agent ends up getting this full reward of 32. So what happened? We removed one edge, and we went from exponentially bad to optimal. So this seems like a very brittle example in that sense. Are all examples like this? So clearly, if we were allowed to remove arbitrarily many edges, we could simply remove anything not on the optimal path, and now our agent behaves optimally. So that's not really an interesting case. What we really want to know is there a trade-off between how many edges you remove and the performance of your agent? Okay? And so the result that we show here is that if we, for any k, we can remove 2e over k edges and get within n to the minus k of optimal. Or in other words, we can remove a constant fraction of the edges and go from exponentially bad to polynomially bad. This is actually not known to be tight. That n to the minus k could be as small as b to the minus k. And this is something that we were not able to solve. The outline for this proof is kind of straightforward. The way to think about it is if you order all the edges on some log scale by the reward on that particular edge, and you consider intervals of width b, if you remove all edges not on the optimal path within some interval, then the intuition is that will motivate the agent to actually follow the optimal path. Now, there are some subtleties involved, and this doesn't actually quite work, but that's the general flavor of the result. And so to summarize, we have found that we have bounds on how sophisticated agents do well with costs. We've shown how they do poorly with rewards. The key feature that distinguishes them from naive agents is that they are time consistent, despite the fact that they actually have time inconsistent perception of costs. Right? The perception of these costs depend on where in the graph they are, or you can think of it as where in time they are, and yet somehow they are able to make plans that are constant with respect to time. So some further directions from here. This was kind of an experiment in separating bias from the awareness of that bias. And so we were able to see that this awareness of the bias actually does have a big effect and can, in fact, be more problematic than the bias itself. Does this generalize to other biases? There's also this question of whether we can get a stronger result for commitment devices. And a broader question that I think might be interesting here is, can we design mechanisms that take into account the fact that our agents are biased? How do we price our gym memberships, taking into account the fact that agents don't want to go to the gym, that type of thing? So these are things that I would encourage you to think about. Yes?
Two questions. So the first one is, I'm a little bit confused by this distinction between costs and rewards.
Mhm.
And I think if one is just making the chaos negative in the other case.
Sure, yeah.
So in that case, for your first result, were you stating that with the assumption that all costs were positive? That always makes
That all the costs are positive. Okay, all costs have the same sign as each other is what I'm,
in both cases.
yeah.
So then one can imagine a graph with some negative weights and positive weights.
Right, so if you're allowed to mix them, then both naive and sophisticated agents can be exponentially bad.
And the second question is, so you're using this technology for moving edges. So do you also improve welfare by adding perceived edges that are never actually traversed?
Yes, actually, this is another thing that we looked at, and it was not as good. Yeah?
So I think from the original Pepper-Gordon paper, I remember like a budgeted scenario where it was like you can never traverse the graph because you have some budget of how much you're allowed to pay when you traverse the graph.
Yeah.
And I wonder how that works in this scenario, especially because you're not doubling the last edge. I think you were just assuming that if you get to the last edge, you take it to the finish. But like, what if there's a budget and you can't take it?
Yeah, so if you're in a scenario where you have to like pay someone to get this job done, like they don't have to traverse this graph, you're paying them some amount, and if they feel like doing it, they will. Really weird things happen. For instance, for a sophisticated agent, the set of rewards for which they're willing to traverse this graph is actually non-monotone. And so there are some examples in the paper that show that. The result about the cost ratio still being bounded by B still holds, but there's some subtleties in like whether or not the agent is actually willing to traverse it for various rewards. Yeah.
Okay.
All right, thank you.
Thank our speaker.